Once in a generation, there was a revolution so large that nobody could stop watching it and take their eyes away.
Welcome to Autonomous Interference. I'm William, this is Ben, and this is Nick. In this video, we're going to show you how we build this beautiful beast.
Come on.
Yeah, it's attracted to it. It's like a bait.
Our challenge was to design a robot that's operating in a warehouse environment, that's able to pick up an item from one place and deliver it to another place. So the challenge was, we've got to figure out where the robot was, and we also need to control the motors to get it from one place to another place.
One of the trickiest parts of this project was managing our time, so this Gantt chart was our Bible. It turned out that this was a complete joke. We assigned 3 weeks to mechanical design, which turned out to be a few days worth of work. More ironically, the design for all the important stuff, camera vision and controller, were only assigned 1 week, which turned out that it took us a whole semester to barely even finish it.
So we broke this problem down into a bunch of subsystems with a finite state machine to govern what should happen at each distinct stage of the robot's operation. We made sure to include a state for each high-level task, like traversing across the arena, receiving an object, and dispensing an object. We kept it simple, minimizing the use of tools like substates, different types of state transitions, and compositions of state machines, God help us. This made our state machine easy to implement and test.
To figure out where we wanted to go, we first had to figure out where we were right now. That part is localization, and the way that we went about localization is using a rotary encoder. This little device that sits in a wheel and counts how many times it takes to make a full revolution. Our encoder let you see 3,600 clicks per revolution. Wow, such high res. Still though, it was an incremental encoder. It wasn't absolute. So to figure out how we were going to figure out our position in an absolute manner, we wanted to fuse this sensor data with a camera vision. In this way, we would use the Kalman filter to fuse our absolute with our relative measurement system. Unfortunately, we had to bail on the idea of the Kalman filter because we ran out of development time. Sad. Using the encoder was good for short distances. We could get from one side of the warehouse to the other side of the warehouse just fine. But for longer distances, the small little errors that built up over time were an error ticking time bomb. So ideally, we wouldn't want to use just the encoder for longer distances traveled. Oh, hi. Speaking of paths, we had to figure out where we wanted to go. This was the path generation algorithm. The one that we ended up using was A*, and the way it works is it looks through every possible combination of paths and it picks the one that is the shortest. It's a greedy algorithm, so it picks the first one that's going to get us from point A to point B. And this worked out to be really, really good. It worked well for us. We picked A* because it was a simple algorithm to follow, it was easy to understand, and it had lots of straight paths, which was going to help our controller. There were plenty of other algorithms that we could have chosen, but this is the way that we chose to go.
We considered lots of different ideas for the controller, from full state feedback to proportional control. We started with PID control since it's simple and reliable. We held the speed of the robot constant and instead took control action on the angular velocity based on the misalignment of the robot with the path and its perpendicular offset from the path. Since the path segments were just long, straight lines that the robot started already aligned with, the control task wasn't too difficult. For this reason, and to save us having to approximate the derivative term in ROS, we dropped the derivative part of the controller. Next, our live robot was having all sorts of problems related to the integral part of the controller. So we dropped the I term from the controller. We saw no set point errors and a satisfactory performance, so a simple P controller was good enough for the linear and rotational controllers.
We have brilliant design. So come have a look. So this is the design we have. When a robot is at a dispenser, we drop the stress ball onto the container. Therefore, we just need to close the motorized gate so the ball is contained inside. So when a robot is in the position of the receptacle, we just open the gate and let the gravity to drag the balls out.
Finally, we've got some things to watch out for and some recommendations. So first of all, expect to put in a significant amount of time early on outside of class to make sure you understand how to work with ROS and Git. For Git, the idea of branches and merging is especially important. For ROS, you need to have a solid grasp of how nodes, topics, and messages all fit together and how the related syntax works. If you don't get on top of these things, they'll get on top of you, believe me. Next is project planning. You're going to want to make sure you understand the bottlenecks to your development and make sure that these are prioritized in your plan. Also, you want to develop by verifying small parts of the larger whole over time, slowly synthesizing it together to produce a combined product that is reliable. Gavin Buskey touches on this in the videos on the LMS, and we recommend you watch those instead of skipping them like we did. Next is that you want to prioritize being able to test things on the ground early. This means getting any form of localization up and running fast, since it's the gateway to being able to test and develop your controller and your state machine. Next, expect to be haunted throughout your development by the fact that your beautiful simulations mean nothing in the real world. Don't be surprised if performance on the robot on the ground is completely different to the simulation of the dynamics. This is one of the main reasons you need plenty of time out on the track. This thing cannot be trusted. So putting all these ideas together, you need to spend time seriously developing a Gantt chart that takes these things into account and then adhere to it from there, making changes only if absolutely necessary. Our Gantt chart was packed together for the project plan assessment and then promptly thrown in the bin. Don't do that, really, don't. Essentially, just look at everything we did and at all times do the exact opposite. Good luck.